How's it going, everyone? Today we're going to be covering Coulomb's law and effective nuclear charge, the second portion of lesson 1.5, and one of the most important sections of this entire unit. So for starters, we look at a proton and an electron, or some particle that's positively charged and some that's negatively charged. When these two particles encounter each other from a certain distance, they will feel an attractive force towards each other. We know that opposite charges will attract each other. If I have two positive particles, they will repel each other. And two negatives will repel each other as well. And these ideas become very, very important in chemistry when we start analyzing trends and different properties of atoms. If I have a region of space, and let's say this is the whole universe, and in this universe there are two specific sections of it. In these two sections, this is the only place where anything is allowed to exist, and I'm going to put one electron into this universe. Well, what happens? Can't exist anywhere out here, so the electron is going to pick one of these two. Which of these two? Doesn't really matter. It'll really pick one at random and stay there. It might go back and forth for a while, but for the most part, it's going to only exist at one space. There's only one electron. Now, what happens if I take that electron and I'm going to add another electron to this universe? Well, now what happens is this electron has to make a choice. Do I go where the first electron is, or do I go where there is no electron? This electron is going to have a natural tendency to fill out the other region of space. Why is that? Everything gravitates towards the lowest energy state possible. It's a more stable structure inherently. Electrons also repel each other. They will not want to be within the same confined space. If they can be far apart from each other, they will choose to do that. So what exactly is Coulomb's law? Coulomb's law lets us quantify what that repulsive force is. Coulomb's law is given as follows. F is equal to K, Q1, Q2, over R squared, where K is the dielectric constant, a constant value. Q1 is going to be the charge of some particle with a charge. Q2 is another particle with a charge, and R squared would be the distance between these two. For this class, you will not be plugging in numbers into this equation and quantifying it. You will be analyzing it more from a qualitative perspective. So Q becomes effectively irrelevant for us. We're never going to use it. You're never going to be concerned with it. You're never going to be asked to actually calculate the value of F. That's more something in physics. Instead, what we're going to do is write a proportion that simplifies this equation and just keeps us the things that we need. We only need Q1, Q2, and R squared. How do we get these values, though? We don't use the actual Coulombic charge of an electron. We call one electron having a charge of -1. And then one proton will have a charge of +1. Those are pretty much all the charged particles you'll be dealing with in the class. Yes, there's ions and all that kind of stuff that have charges, but they're composed of this. Now, if I had a proton right here and an electron right here with this distance being R, then Coulomb's law would turn into this proportion for Coulomb's law. I'd put a -1 right here for one particle, +1 for the other particle, and then that distance R squared. Applied to actual chemical ideas. Let's say we have an atom. This atom is going to have 3 protons in the center. The first energy level is going to be completely filled. So I only have 2 electrons in the first energy level. Then I'm going to put 1 electron in the second energy level. And let's imagine we try to grab this electron and take it away. Just move it somewhere else. We're trying to pull that electron away from the atom. How hard would it be to do that in the beginning? What is that attractive or repulsive force, or whatever is this force between the two things? Okay, well, let's see. That proportion for Coulomb's law is going to be Q1, Q2 over R squared. Q1 we can obviously call the electron. Let's just say we're going to call it the electron. Why? Because that's the particle we're dealing with. It is this electron right here. But then Q2, what does that become? Do we assign it to another electron, say this electron right here in the energy level, or what do we do? Well, the problem is the real answer would be the sum of all the interactions that are present. So pretty much everything that's going on here, the interactions between the electrons and the protons. I know I have that electron, I have 3 protons in total, and then 2 other electrons. These guys have a charge of +3 and this will have a charge of -2, but what do? Well, we need to calculate an effective nuclear charge. The effective nuclear charge is the charge that a valence electron feels as a result of everything else. The valence electron being the outermost electron. So at any point in time, whatever is the outermost electron, that electron is in the last energy level. That feels portion though, there's something called shielding. Shielding is the sum of the effects that these electrons are going to have, canceling out that proton, the charge that the electron feels towards the nucleus, the protons in the nucleus. Shielding says that you can actually add these values and cancel them out only if they are inside that region. So we're removing this electron, we have to look at everything inside of this electron. Then Q2 is actually going to be your effective nuclear charge. So how do you calculate this? Well, my electron feels a pull towards the center from 3 protons. So that is a value of +3. At the same time, there are 2 shielding electrons involved. So I will have a -2 attached here. This ends up being a net force of +1. And that becomes Q2. Now if I go back to Coulomb's law, I can call -1, the value I had before, for the charge of the electron, +1, the effective nuclear charge. This is again the electron. And then R squared just being that distance. And that's all for this example. We'll be going much more in depth into different versions of calculations for effective nuclear charge and why it is so important when we're covering the topic of periodic trends in lesson 1.7. Don't forget to subscribe and hit the like button, and I'll see you guys next time.